Okay, so we left off here, 17.4, talking about the Nernst equation. It's named after an actual man. That's why it's kind of a weird spelling. So if we calculate the standard potential E naught for a cell, and that value is positive, what does it mean? Well, it means that we can do work with that cell, that cell will act as a battery and it will give us out energy. It will be a spontaneous reaction. And so for a galvanic cell, the cell potential must be positive. And you should write that down. Because if it is negative, then you've made a mistake if it's supposed to be a galvanic cell. If it is an electrolytic cell and it's positive, you've also made a mistake. So if it's galvanic or we're going to have a spontaneous reaction, delta G would be negative and E naught would be positive. So you should write down those relationships. So if it is negative, then it is non-spontaneous, and that would make it an electrolytic cell, and we would be plating something, and we have to supply that energy to the battery. So E naught, delta G naught, and K are all measures of whether a reaction is spontaneous or not. So if E naught is positive, delta G will be negative, and K will be greater than 1, then it will be spontaneous. All of those things correlate together, and if you look at the equations, I think you can figure out why. And so we're going to talk about the variables in a little bit. In fact, here they are. So delta G is equal to negative N Fe, and E naught is the cell potential that you now know how to calculate. F is Faraday's constant, and it is just a number that makes this relationship work out mathematically, and it's always that number, so Faraday got to name it after himself. And N is the number of electrons that are being transferred in that reaction. So that's why we have to be able to balance those equations, is so we can know how many electrons. And so if when you were doing your balancing you had to multiply equation by 2 or 3, that N wouldn't be just the 2 electrons transferred, but if you multiplied it by 3, then it would be 6. So you do have to take care of the number of electrons in the Nernst equation. So if you look at this equation, we can see that if E naught is positive, then delta G has to be negative because we're multiplying. When we use the number of electrons, we do not make the electrons negative. It's just the number of electrons being transferred. And it's the number of moles of electrons. If we are talking about an equilibrium expression and we know K, then we can figure out E naught, which is kind of helpful. And that would be that E naught is equal to RT divided by the number of electrons being transferred divided by Faraday's constant times the natural log of K. So if I gave you the cell potential, you could figure out K. And you have to remember here that the R value is not the one that has liters, moles, atmospheres, Kelvin. This is the one that has joules in it. So you do need to make sure that you use the correct value for R. And that would be something I would want to write on my one-page wonder, my sheet that I would use for this chapter. So, and that value for R is 8.31 joules divided by moles times Kelvin. Temperature has to be in Kelvin because we can't have negative temperatures in these calculations. And then Faraday's constant, you see that the joules cancel out, the moles cancel out, we're left with volts. Kelvin also cancel out. And so if we know the cell potential and we divide it by the number of electrons being transferred, that would give us the inverse of the log. So if K is positive, we get a value for E naught that is greater than 1. If E naught is negative, then K has to be less than 1. So here's the relationship, and I think this would be a good one to put down in your notes as well. If you want to go between delta G, let's say over here, and we want to go to K, then we would use this equation, delta G equals rat link is the way I think of it. If I want to go from delta G to E naught, I use the Nernst equation. And if I want to go from E to K, I use this equation here. So there are three equations, there are three things I can ask you for, and I think that's fairly straightforward. I have to give you at least, like if I started and gave you K, then you could calculate delta G for me. Once you have delta G, you can figure out E naught. If I give you E naught, you can figure out delta G, and you can take delta G to figure out K. If I give you K, you can figure out E naught. I think you get the idea. So, at this point, we've only dealt with standard reduction potentials. And that means that our gases are at 1 atmosphere pressure, and that our aqueous substances are at 1 molar. We can have conditions, however, where it is not at standard cell potential. It's not E naught or delta G naught. And it would work the same way, but those concentrations would affect those values. So the voltage will increase, and this is definitely something I would have in my notes. The voltage will increase if it becomes it will become more spontaneous if the reaction concentration of reactant is increased or the concentration of product is decreased. And this is getting back to Le Chatelier's principle. Voltage will decrease or become less spontaneous if the concentration of a reactant is decreased or the concentration of a product is increased. So here is our equation. If we know R and T at 298, we can figure out what that constant, and we could put in Faraday's constant, and we kind of reduce this Nernst equation into something a little bit more manageable, so that all we have to do is either put in Q or cell or the E naught, and you would be able to figure out the cell potential or Q. And so we're using Q here because it's not at constant instead of K. So I'm going to talk about electrolysis in the next video. Thank you for watching, and I'll see you soon.